Hello, welcome everybody. My name is Joanna Rutkowska. This is Alexander Teroshkin. We represent Invisible Things Lab here. Invisible Things Lab is a consulting company. We focus basically on operating system security research. You can find more about us at this address. Today we're going to talk about two things. We're going to talk about Vista kernel protection and why it doesn't work. And also we're going to talk about virtualization-based malware. And you'll see what are we up to actually. Does it work okay? You hear me everybody well? Yeah? Okay. So digital signatures for kernel drivers in Vista. As you all know, Vista has a requirement that all the drivers needs to be signed and even administrator cannot load them. These are the quotes from the official Microsoft documents that explain the reasons that Microsoft decided to implement it. Because as we know, it's a very controversial feature because many people complained that why they actually need to buy a certificate if it's like their own computer. If it's their own computer, they should be able to load whatever they want. And Microsoft doesn't allow them to do that. So Microsoft replies in such a way that they believe digital signatures are an important way of kernel software, are an important way to ensure security of computer systems, and also that they increase safety and stability. Even users with administrator privileges cannot load unsigned code on x64-bit systems. Last year here in Vegas, I presented pagefall attack, which just relied on some design problem in Windows that allowed a user mod process to actually load unsigned code into Vista. That has been fixed a couple of months later in Vista RC2 by Microsoft changing a little bit the API used for accessing row sectors. Right now, it's not possible to, at least on Vista 64, it's not possible to open row disk access to a volume without first locking the volume. And in order to lock the volume cannot have any open file. So obviously we cannot open row access to a volume which contains page file because page file is opened. So for today we came up with some other attacks. Well, the attacks we're going to present are pretty obvious from the philosophical point of view. It's just Vista, like all other general purpose operating systems, like Linux, FreeBSD, it's a huge monolithic kernel design. There are like hundreds of, or thousands, or maybe tens of thousands third-party drivers available that are signed and then could be loaded into Vista without any problem. Many of them are poorly written. Now Alex will tell you some more. We'll present you two examples of two bugs that we found in some commonly used drivers. Yeah.
As you know, many drivers have interfaces for calling some of the kernel mode code from user mode. This driver, which presented on the slide, is included in the ATI Catalyst package, and it has a few interfaces for reading and writing kernel mode memory from user mode. Actually, as you of course know, only administrators can install drivers. So only administrator can use this interface if there was no such driver loaded before the attack. So if you consider old days when XP was running, for example, there was no such problem, no such security problem, because administrator could really install any driver. And if a driver developer has to implement some features which can't be used by operating system interfaces, it was okay to implement such interfaces using driver agents. But for now, when administrator cannot install unsigned code, it became a security problem, because if an attacker can find some vulnerable driver which was signed by a valid certificate, it can install it, of course, because it's signed, and then abuse its interfaces to do some attacks. For example, this one can be used to overwrite any byte of kernel memory from administrator account, of course. So, for example, we may overwrite the variable which controls the behavior of Vista, and it enables or disables the feature of driver signature enforcement. This is the code that actually validates the image of the driver, and first it tests the value of GCI enabled variable, which can be easily overwritten by the exploit which used, for example, ATI driver. Here's the certificate of this driver. You see that it is valid, and if attacker has the binary of such a vulnerable driver, it can easily install it. Consider another type of bugs. These bugs are not used for reading or writing memory from kernel, but, for example, this driver, which was included in NVIDIA Enforce driver package, actually in Entune software, is able to read and write MSR registers, machine-specific registers, on the command which was passed from user mode. Administrator can install this driver because it's signed, and user interfaces like this one, using ordinary device user control routines. And you see there is no any checks for the number of the machine-specific register which is being read or written. So an attacker can specify, for example, L* register, and it may overwrite it with any value, and we have a shellcode for it. Look at the shellcode. We may set the L* value pointing to this shellcode which is located in user mode and execute it. First thing that this shellcode will do is to restore the original value of L* register. And after this, it will be safe to perform any syscall instructions from our processors, of course. But we already have our shellcode executed with kernel mode privileges. So we may do here basically anything. And what we do here is we allocate a memory for the executable code, copy the driver code there, and run its entry point. I assume this driver image was a portable executable image. So we may load and run virtually any driver, even if it is unsigned, of course. This is the slight update of the previous shellcode. It allocates a kernel mode stack for it. This is because a few Vista functions check for the stack, which is currently used by the CPU. And for example, we cannot create any kernel mode threads without allocating kernel mode stack for the functions. So this shellcode is actually used in an exploit which can load any unsigned code in Vista.
Okay, just one more clarification for those people who are actually less technical. So the whole problem, for example, in this driver is basically, well, this is a routine which is called in a response to a IOCTL sent to a driver from a user mod code. Normally drivers exposes lots of interfaces like this. The problem here is that basically this driver does not do the proper check, because here a user mod process can simply ask a driver to do a write to MSR register, an arbitrary MSR register, and the driver should not allow for that. This is the problem here. Okay, so I'm sorry, I'm speeding up because we have like 120 slides for today. So I try to... Sorry, we got a lot of stuff actually. A quick consideration. You might be thinking, okay, if we have like not a buggy driver, like we don't have a buggy, if we don't have a hardware for which like NVIDIA or whatever those bugs were, then maybe we should be not afraid. This is not a problem. This is not a case just because the hardware actually, the driver actually does not need to be present on the target system. The attacker can actually bundle the driver to its rootkit pack, and just the first thing he or she will do is just load the buggy driver, which Vista will allow to do because the driver is signed and there is no reason not to allow for it to load, and then it will exploit the driver back, and then will load other unsigned code like rootkit.com. The nice thing about this shellcode, which Alex also didn't mention, was that it allows us to load any pe.sys driver unsigned, and the loading does not involve official API by the operating system, which is used for loading drivers. So even if we have host IPS that is supposed to filter our driver or control driver loading, this all happens beside it. So it doesn't matter actually whether we exploit a problem in a popular driver or not popular driver. These are actually pretty popular, but we could find some exotic driver in some stupid keyboard, and always we can bring it to the target system and load it and exploit it. Okay, imagine an ideal world when all the developers for Vista drivers will be writing bug-free code. Still, we can get around this because it's possible to. Because the Microsoft does not require people to submit drivers for signing, all I have to do as a developer is to buy a certificate for signing. And I actually spent 2 hours doing that. It costed me $250. I just went to Global Sign. I just applied for a certificate. I put my official company name, Invisible Things Lab. I put my official name. They asked me to send this form. I need to sign it. I need to provide the company registration form, plus my ID, and send them by fax. And after 2 hours, they send me back my certificate. We have it right now. Invisible Things Lab. You see that we have a private key. We can sign whatever code we want. Obviously, it wouldn't be wise for anybody to sign like a malicious code. However, nobody can prove me that I can write some tool for kernel which would be doing something. I don't know, would be a process monitor, for example. And I can make unintentionally a subtle bug there, like a buffer overflow, whatever. And then I can put this driver on my website and make it public. But nobody will know about the driver. And then I can actually use this driver, bundle it to my rootkit, and again, load the driver first, exploit the bug, load the rootkit. Even if somebody finds out that actually the rootkit uses a driver signed by Invisible Things Lab, nobody can actually prove me that the bug I did was intentional, because we all know that software developers do a lot of bugs. However, we don't have to do this right now because we have dozens of bugs in those drivers. Alex finds them in his spare time, and it's really easy. I'm going to skip some of the slides. This presentation will be available for download. I will give you a link later so you can walk through all the slides later. One of the solutions, probably the most elegant solution to this problem, the problem of securing a kernel of the operating system, so the problem of making sure the integrity of the operating system, the solution is to use a microkernel-based operating system. For example, if you look at Minix 3, it's an operating system which keeps all the drivers in user mode in their own address spaces. One nice step made by Microsoft is something which is called UMDF, User Mode Driver Framework, which allows to keep some of the drivers, some PDAs drivers, USB drivers, in user mode processes as well. However, this is very, very immature solution right now. Immature in the sense of that there are just 3 classes of drivers you can put there maybe, and all other drivers like keyboard, like graphics card drivers, network drivers, everything else should be real drivers in kernel. The message of this part is basically that we don't believe it's possible to create an effective